So yeah, good afternoon. So yeah, today we will be like a demo session is on backlight imaging, simple technique. So right, so as I said, like all we need is a light source. Test section. Yesterday we saw Schlieren and a bit like if you remove the knife edge shadow graph was there. So today we will have a simple this thing like a backlight imaging. So we'll show like how to calibrate it, right? Since we were talking about the calibration, converting the pixel into millimeters or the size, and then some processing also. Vignesh will show you like how to process and get the information about size information or size distribution. So all that. So if we look at here, all we need is the one light source. So right, there is a small high power light source is there, right? So then we have again to smoothen it out. We want to have like a diffuser. So this is nothing but again a frosted glass. So this will rip, or you can even use a white paper also. So that is good enough. And then this here will be the test section kind of thing. And then we have a camera and attached to a small lens. So right. So this is the simple setup. And then if you put anything here, that will create a shadow on that. So which we will be able to see here. Yes, switch on. It takes little time to get connected. Did it come? Click. No. So this is the camera, this capturing yesterday we saw. So at the moment, okay, we can. So we have low light intensity. So maybe morning I was telling, right, if we go to the higher frame rate, so light intensity will reduce. Maybe slowly open other direction. Not saturated, right? So this is at the moment we put 5,400 frames per second. So by default, what happens if you have some frame rate? 1 over that frame rate will be the exposure. So if you want to like you can change here the like if you reduce the exposure to 1 over lakh, you don't see anything. So now though the frame rate is same, now reducing the exposure, so it is eating away a lot of light because you're exposing the sensor for very short duration. That light is not sufficient. So if you need, can you increase slowly increase? Yeah, look at there and one more, one more, one more. Like a full is it? So even then, so almost like earlier initially, how much was that? Right. Yeah. Mhm. So now initially it was 10% or how much? So 10, we increased to 100% of the intensity. Right? No, full bit. Yes, yes, yes. When we increase to 100% also, like this is 1 over 1 lakh. So still not able to see. So then the only way is to increase the exposure. Yeah. So now we start seeing some light, right? Like this. Okay. So this is just to explain like the importance of exposure. So maybe for the kind of thing we are looking at, we don't require this much exposure. Maybe you can reduce. So we'll go back to 1 hour FPS. We are getting. No, reduce. There is a loss, right? So now this is the like a field of view, right? So if you measure like without any calibration, we can, so we need to stop to measure. Okay, we'll put the calibration. So we have a small scale here. So the scale, like when you're not, so if you are measuring large field of view, we can use this scale. So easily large field of view, there's small error. But if you're measuring a very small field of view, so then what happens if you're focusing on a very small area? So the any error will associate with a couple of pixels. Like the scale marking has some width, right? So that will induce error. So you need to get a other kind of a scale. So there is a tiny. If you look at this glass, right? So there are small markings here, right? Total is 2 centimeters divided into how many lines? So we have quite a number of. So it's focal, yeah. So this length has a length has 300 focal length. So if you see here, it is 1 centimeter. Okay, this says inches. Yes, inches, sir. But it is like 1 centimeter. Okay. This side it is 1 centimeter. This total is 1 centimeter. Okay. If you just record, you can remove the scale, so we can zoom in and then do the calibration. So we can calibrate. Now, if I take this, right, so this location, so we know this. At this pixels and this distance, we can directly do the calibration of calibrate. So length between two. Calibration very good. So but this needs to be straight. Try it. You have to try it. Yeah, that we can give it as a. So 20 micron. Yeah. So now this got 0.0198 per pixel, right? So which is about 20 micron per pixel. So if you want to capture any drops, so it has to be about 50 micron or above 50 or 100 microns. You can capture anything below that, you will not be able to capture it. So now we go live, it will appear. Okay. So now we look at some simple spray from this book. Yeah. Okay, yeah. So you can just look at the drop. Maybe Vignesh, you can explain. Yeah.
So to start with, like how the magnification is, like we can see, like we can check in the needle. Like we can see.
Vignesh, you can even see this, right? Prevent anything.
So we can see, like, okay. So we have this. So like we can see how, like I am going into focus. You can see. So if we want to see like droplet, so if we want to measure the size of the droplet, we can record it. So now we can check the size of the droplet. So we know the calibration already. With the help of measurements, we can go like diameter. So we can select 3 points around the circumference. So it is like approximate diameter. It is like 2 mm, 2.48 mm. So this is one way directly, like seeing it, like from the PFE software itself. We are just seeing like what is the size of the drop. It works like approximately. It works when there is a single droplet. Like if you have a group of droplets, we have to go for image processing. At the time, let us say for that, what we can do is like for demonstration, we got a spray here. So with this, we are going to demonstrate. So we will take this out. So
We'll go back to normal.
So we are going back. So from the measurement plus the diameter, so we can take it is like just based upon the software only. It is like taking through 3 points around the circumference. It first it will take into pixel. Then we know the calibration value. Then it becomes the mm. So only yeah, there it is coming. So only if you know the calibration value, it will give in mm. Otherwise, it gives in pixel. So this is directly inbuilt in software. So otherwise, if you want to take, like consider between 2 points, what is the value? So you can take the like point. So let us say 2 points are there. So here you can see in the like point itself, you can see that is a pixel value. 8, 7. This is a pixel value. Or now it is there in the this one, mm, I guess.
This is in mm already since you calibrated.
Since we calibrated, it is going in the mm. And again, if you see the total is around.
This white area is about.
White area should be around
1 centimeter.
1 centimeter roughly. So now coming back. So now we will check with like a small spray, like we will see how the droplets are coming. Maybe one more time.
Didn't require. There are few but not focused.
And there are, you can see there is a streak. Like there are two. Maybe we can come again.
Now, just you can show that depth of focus also. See, now earlier, like last, okay. So, yes, I think I have this. So, yesterday we saw that, right? Depth of focus was quite large because that lens is a like a large focal length. So then the short focal length 50 has a lot of focus. So now if you look, if you want to see the depth of focus,
Small field of view records like
yeah,
time.
okay. So now you can look there slightly this way, that way, it'll get defocused. So you have very narrow depth of focus. So probably of the order few millimeters. So anything of that plane will have will not be get focused. So we'll go back to, I'll just show that in the memory, the images were not in the plane, right? So we can just have a look at, uh, he sprayed, I'll just play. Yeah, they are there like, so all those drops are moving, right? But since they are not, they are out of focus, they look like something. So the one which came here, it is also, yeah, even here, like, so look, this is the motion blur we were talking about, right? So it is a drop. So in one, within this exposure time, so it moved here. So it just created a streak. So then you may say, like, is it a ligament, or is it really a ligament, or it is a streak, right? So one easy thing to identify is, if it is a streak, so it just look like a perfect cylinder. It is just like a drop move in this direction. If it is a ligament, you have some undulations. That also you can easily get it. So this shows that, so probably or maybe next time in a focus thing also we will see, if we still get a streaks, then we need to increase the or reduce the shutter speed. See the speed of the camera, you need not worry about it, it is capturing. But exposure, if you reduce, then so you will be able to freeze the motion. Maybe can keep live mode. If you know the velocity, you can calculate. So you can get the, let's say if something is moving at 10 meters per second, you know that this caliber. Now we got 20 micron per pixel, right? So 20 micron per pixel means within the exposure time. What exposure time we have? 1 over 9,000, roughly 1 over 10,000. So that means about 10, no, 100 microseconds. 100 microseconds. So within 100 microsecond, if it moves by more than a couple of pixels, so it will get a blur. So let's say 2 3 pixels if it moves. So that means like 2 3 pixels is about, let's say 5 pixels if you take. So 5 pixels is how much? It is like 20 micron, 100 micron. So 100 microseconds, if it moves 100 pixels, it will streak. So the velocity you can calculate 100 microseconds by 100. So that will be the velocity. If you expect that velocity, you will get, or anything above that will streak. So if it is below, then it will not create a streak. So then, otherwise, then if it is too much velocity, then you reduce the exposure further. If you reduce the exposure, then we have to have, no, you have to, in a focal, just put that as a, yeah, yeah, yeah. Record, yeah, no, reduce. Wait. They are there. I think we give it a try. Let's have a little. I think you did before, I think. Or was it? Yeah, here also we can see that. So we have a lot of drops. So everything has, though they are like here, they are focused, right? Look, but still there is a motion blur. All of them, like in this drop, this is like quite focused, right? But there is a, now how to remove this thing? Cancel it. Side. Okay. Other one. So all this, let's, if that is the case, then so we reduce the or we reduce the exposure, right? So it was 1/9,000, right? So it is quite a motion blur. Let's say we go to 1 hour, so double, like roughly. So the moment we go, like we have a reduction in light. Now you can increase the. Full. Okay. Yeah, reduce. 92,000. Okay. Yeah, now 80, almost 10 times. Now exposure is reduced by 10 times. So earlier 1/9,000, right? So now we are 1/83,000. So should reduce the motion blur. Okay. Yeah. Here again, if they are in focus, no, this is not a blur, right? This is a blob. So you can clearly see that, right? So okay, if this is pixelated anyway, the resolution is that, but it doesn't look like a motion blur. So right, so it is not like coming like this. So then we can see the other drops. Yeah, like here you have so many drops. So there is, so the, and you can clearly see that there is a sharp boundary here. So there is no motion blur. So now you have so many drops. So you can take these images and then, so now you are able to see that individual drops. So we have a calibration. Use, Vignesh will show you how to process the images using a MATLAB code. So then again, so we know that this is 1/9,000 FPS. So that means what is the time between two frames? So this is 9,000 FPS. So right, 1/90 milliseconds. We're like, okay, no need to get the numbers. It is 1/90 milliseconds. So, right, you know the time between. So, if I take this, okay, let's say zoom into a very small area. Like this is one frame, this is next frame, right? This is previous frame and next frame. I can take these two frames. Now I know the time. Then I can find what is the distance moved by, let's say, this drop. We all know like this drop is moving here. So, right? So, based on that, we can calculate the velocity. So, the problem comes, so here it is fine. There are different size drops. What if you have a uniform size drops all over? Right? They're hard to distinguish. That is a, we have, I don't know, we can maybe tomorrow we can show that. So, if you have a monodispersed drops, you try to process the drop, it will give all directions. One will identify this. So, that's the way sprays, it is easy. So, if you have a different size drops, it is easy to get. Yeah. And also, you can correlate the yesterday what we were like. If you look at this drop image, everything is black except at the center, right? Like because of the refractive index, light bends, and then it acts like you have a lens sitting over there, and try to focus at the center. You get it. So here, like this is nearly closer to spherical. So then you can see this. So you can even see here. Then these are like big blobs, ligaments, and then there is like a really fine spray and like really fine mist kind of. And this one is out of focal plane. So you in a processing you can always remove all this. There are methods to remove, like if there is a sharp edge, then only you consider. If this blurring is there, so usually what they do is put a cutoffs of thresholds. So right, if you put a high threshold cutoff and so this is defocused, right? There will be a one area, sharp area, and then there will be a slightly defocused drop that will. Mhm. Yeah, or this one, like you have high intensity here, and then they're low intensity, like little bit of a gray area, right? If this based on the gradient, if it is focused, this gradient will be really sharp, right? So you have edge, and after that nothing. If it is defocused, then this gradient will be slowly, gradually moved. So based on the steepness of the gradient, you can say like how much you need to consider, how much you need to like at up to what extent you can reject. Yeah, you want to show the processing? Anything else you thought of? Okay. Huh.
I called it A,
Uh-huh.
and then second frame,
Uh-huh.
it moved some distance.
Huh.
So the same drop A.
Yeah.
So I measured velocity and
Yes. Yes.
and is that one reading is enough?
No, if you want to get like different size of drops will have different velocities. So you need to process and get, say, the velocity of like this drop size. This is the velocity. If you want to take an average velocity, yeah. So then again, this is the size of the drops. Then they will have average velocity. And the morning, as I was telling, like in a spray, if you have a different size drops with smaller size, they lose momentum very quickly. So their velocity will reduce, like suddenly they'll stop, and after some time, so and with larger size they travel bit more. So yeah, you will not have a single velocity, ma'am. So there will be a, you'll get like sort of a velocity field or size versus velocity. If you plot, you get all the scattered, and then same size drops at different places may have different velocity also. So that is also like, if I say 100 micron will drop in a spray, all the sprays will not have same velocity. So there will be a different velocity. So it depends on, like if the spray is like this, so over the edges they will have some velocity. At the center they have some velocity. So you will have all like full scattered this thing. So it'll not be direct representation. Otherwise you have to take a mean velocity. That will all the statistics.
The contact, the angle between the droplet and this surface. Suppose this needle is made.
Yeah, you can.
Can I measure the contact angle between the droplet and this line?
Yes, definitely. You have a surface, right? So that's how the contact angle measurement works. This is the same principle. They will have a light and the camera. You need not have a high speed camera. You will just normal camera will do. So that, and then you can just fit and measure the contact angle. That contact angle measurement, or from that you get surface tension. Surface tension measurements, they do that. Or this pendant drop, they'll have a small needle and drop will be forming, and just before it comes down, so you can measure the surface tension. Yeah, Vignesh will show you about the process. If not the same images, I think we'll, rather than using this images, converting it, we'll show some other image. So, process
So
will
we will save this image. Also, first we have to take the background. So we will take the background. This we can process it later. So I have some image previously taken, previously processed. I will explain all the things like what we used to do generally to get the drop sizes. It is basically image processing only. It is like we take a background. From the background, we can subtract it. Whatever is the background, like whatever the object in front, we get. Otherwise, all the background is subtracted. So we get information like white or black region, whichever based upon our subtraction, we get it. That white area or dark area, finally, we get the size of those white area as well as this drop area. So first we have to take the background. This images also we will take it, we will save it. This also we will process it at the end. Before that, I have some image. I will just show the processing because every image may need a little bit of like thresholding value we may need to change. This may take some time. So that first we will take the existing images, we will process it. After that, we will go to this image. So before that, for processing this image, we have to get the background file and the calibration file. Calibration we know, like 20 micron per pixel. 20 micron pixel, we can say like based on the sensor also. Like sensor is like 20 micron plus 20 micron, the sensor. So this lens is 1:1. So 1:1 means we get like this, like square will be like 20 micron, whatever is the sensor we are going to get. So it is like 5:1 means we can get like 4 mm. Sorry, I am say, did I say 20 mm?
Yeah, like
Oh, the sensor is 20 mm. Did I say 20 mm or 20 micrometer? 20 mm. 20 mm. So the sensor is 20 mm cross 20 mm. So that's why we got 20 micron per pixel. So the resolution is 1024 cross 1024. The total is like 20 mm. 20 into 1000, 20 micron into 1000, we get 20 mm, is it? So the sensor total is 20 mm. And we see whatever we are seeing in this one is only around 10 or something. Okay. So first we will take the background. So this image we will save it. Background also we will save it. So we take the
yeah. So empty ones we can take it as a background. No need to
Okay.
again record, right? So here it is. So there are no sprays. Yeah, this thing
Yeah.
we can consider as a background.
Background. Yes.
Yeah. So because again, sometimes what happens if you have to start the light, you don't know which position you are there. Sometimes you forget. So we can consider this where there is a spray as this one. Other ones we can take it as a background.
So this we can save it. First 10 frames maybe.
Yeah.
This we can save it as background. So first I have saved the background. Then I am going to the required region where I want to see the droplets.
Yeah, remember that it takes a lot of memory. So 1024 by 1000 were like roughly about 1 MB, right? So each image is 1 MB. So then if you save it 1000 images, so 1000 MB.
Yes. So we are saving it. Only the required region we are saving it. Wherever the droplet is there, we are going to save it. Ah,
Yeah.
okay. So generally we take TIFF images. So previously also I saved it as TIFF. I will go and save it as like previously I saved it as MP4 file. Now I will save it. So it takes time. Anyway, it goes saves.
Camera is there. Eight. Hmm. Hmm. Mhm. It's like extra protection, right? It is like See, if you are interested in the gradation, then you will have, yeah, those kind of things will- here it just seems to be like a boundary edge.
Okay, just close.
It's already clear.
So we have saved it. We can just check it once again. So here is a case one. We can have like image by image. We have image by image set, data set. So also we have the background. So from the background, we are going to subtract. Before that, as I said earlier, we will start with some existing images.
Of cameras,
Yes.
because each of the cameras or something it's heated up. Yeah.
So we have image sets. Actually, while using this processing, what we need is image sets. So if we want to extract droplet size information only, we can have single image. If you want to get velocities, we need set of images. So what we can so what I saved here is like sets, images and sets. So we have set one. Let us say there is a one image, and again we have, let us say, set two. So we have one more image. So we can see the images like droplets moved from there to here. Okay. So it is completely a new set. So you can see there's droplets. Previously, the droplets was coming from here to here. The images I am showing you is from top to down. Okay. So you can see in the previous image, the droplets are here. In the next image, droplets went down. So it is moving from top to bottom. So we are going to extract droplet size, droplet velocity. This code we have here is available online. This is developed by Anand, Professor Anand. He was earlier in IIT Madras. He is colleague of Madan sir in IISc. So we added few information like how to extract the velocity and other things we have added it. So this maybe we can share it if some of you need it. We can share this code here. Okay. So what we are going to do is, so I will open the code. So we can see. So for checking, I will just start the code. So it is processing. So it will give the information directly. This code is like, I'm just showing the input output starting, like initially what is the input, what is the output I'm showing. So we are going to give like two sets of file. 1 to 2 means two sets of files we are going to give. Droplet size information, droplet velocity we are going to get. So we have got information like relative span factor, DCV10, DCV50. These are all like how the droplet size distribution is there. So let us say DCV10. DCV10 is 10% of the droplet volume lies below this diameter. So around 10% of the droplet volume lies below 360 around microns. DCV90 is again like 90% of the volume. So our close to 10% to 90% of volume of the droplets lies between 300 to 800 microns. Apart from that relative span factor, there is a formula. You can go and check it. It is like span, like DCV90 minus DCV10 by DCV50. It is like a span, like how much droplets is how much it is distributed. Apart from that, we have SMD. This gives the information of volume to surface area of overall droplets. These things you can go and check it later. So
assembly model we discussed.
Okay.
RSF also.
So velocity also is here. So now we will see the processed image. So this is a processed image. As Sir said earlier, so we in this code what we give is like area cutoff we give, like
Yeah. So this code was developed. It is there freely available, developed by a group, Dr. TNC Anand group.
Sir,
just now, sir.
Okay. Yeah, you mentioned it, right? It is there in GitHub.
GitHub. We made few changes to add the velocity. That also we can, if you want, we can show.
Yeah.
We can share it with you over request. So this we can see whatever the images or like whatever the droplets which are focused, it is marked in yellow. So whatever which are focused, it is marked like within like pink and like magenta color. Okay. So it will take only the droplets which are focused. So it will in the first frame, if it's focused, it will take. The next frame, if it is focused, it will take. Between this, what is the velocity? That is what you're seeing here. Also, we have velocity vectors here. So I can show you velocity vectors. So as I said earlier, only the focused droplets, we get the velocity vector. Okay. Other droplets, it is not taken. Only the focused droplets, we are seeing the velocity vector. So you can see for each image, you can see the velocity vectors. So you know the velocity, you know the droplet size information from our this code, we get it. So now I come back and show you like how this code works. So there is a lot of information is there being fed in this code. So first, what we are going to give is what is a file name and other things we are going to feed. And for velocity, we need time between each image set. So we need once you get the distance between centroid of one droplet to the centroid of the next droplet, you know the distance. You need the time del x by del t or del y by del t. You need it, is it? So we give the dt. After that, you need the scale, is it? Whatever the information you are extracting is pixel. So if you want in mm or microns, you need to convert into like equivalent value, whatever you need. So scale you need to. Scale is nothing but the calibration what you got here. For the images we took, it is 20 micron per pixel. For this data set which we are processing, it is 42.3 micron per pixel. So there it is proportional. It is 1024 cross 1024, 42 into 1000. So the field of view is 42,000 micron plus 42,000 micron. It is like 42, what do you say, 42 mm, 40 cross 40 mm around.
And the frame rate also, you can see that it was frame is 2000, 1 over 2000.
Yes. Frame is like 2000 frame per second. It was there. So TT, similarly, time between two image set is 1 by 2000. So in this, we have to give distance cutoff. So there are two methods to get the velocity. One is cross correlation. You mentioned cross correlation. Cross correlation between the two frames. Cross correlation works based on the intensity. So you take a region, small region. In the next data set, you take another region, like same region. You do like cross correlation, like FFT and IFFT. So you get the peak. Wherever the peak, it is said that it is mapped to that region. So the cross correlation works like that. But here we have drops like all over, different scattered at different places. Cross correlation may not work here. So what we are doing is we take the information of the blobs. So we are giving different conditions. So you check this, you check that, like different conditions you give. So distance cutoff is nothing but there is a in the first frame there is a droplet at some one position. In the next frame there is a droplet at other position. So you consider only if the droplet is within this distance. So you cut off one.
So maximum expected movement, I think it is mentioned there, right?
Yeah.
So beyond that, you expect that any drop, we saw that different drops will have different velocity. This is the maximum distance any drop can move. So otherwise, what happens if you have a similar drops of two sizes, one moved here, but there is another one moved. If you don't give this maximum cutoff, this will show that this moved here rather than mapping to that, this moved there. So which gives spurious
vectors. So again, we are going to give X cutoff, Y cutoff, like X displacement, or how maximum it should go. In our case, you saw like it was going this way only. So it is not expected that it is good. So some physically few things know that we are going to give us input. So it is like expected. So again, Y cutoff we have. Y cutoff is this distance, vertical distance. Again, area cutoff we have to give. So we have two, like let us say droplet 1 in first image, droplet 2 in the next image. So it will match the area only with which is 10% of area change is there. It will detect. So only all the conditions are satisfied. It will go to the velocity measurement.
Yes. How much we sometimes if there is a slightly non-spherical drop, it is turning like this. So if the area is within 10% only, it will consider. You can change that. We say that, okay, I'm okay with, sometimes you will not get really perfect images, but still I want to get a ballpark number. You can relax this parameter, but the errors will go up.
So another is bounding box limitation, they say. Bounding boxes, you can see later, like there will be a like circle or like oval, like we will create a bounding box, like maximum extension. Like towards this, we will fix the maximum. The code works like this. Once you put like BW area, some command is there. Once you put it, you get all this information, like bounding box, area, like white area, everything you get it. So this works based on the image processing in the background. Okay. So these are the things we are giving as setting. Only if this is satisfied, you find the velocity. Otherwise, you just ignore it. Okay. So it is like input. It is well.
We are getting correct. Is it correct?
Yeah, that you can check from the image itself. You can check. The first image, you get the centroid. What is the pixel value? Next image, you get the centroid. What is the pixel value? You know the distance. You get the velocity. You check the velocity. That is one way. The code also works like that only. Okay, background it is working like that only. So other parameters like where to put the like this directory, where to choose it, like background file, what is the background file we are going to give it. So percentage, it is like thresholding percentage, how much percentage we are going to make. So this is like what is the percentage? Like it says there are different ways. Like one is Otsu threshold criteria. It gets like optimal value of threshold. So you have an image. So you have to give the, like, let us say one value. After that, whatever is it, you consider black. Remaining, you consider it white. It is like filter. Maybe I'm putting it correctly. Threshold, like
Yeah.
like you're choosing whatever the pixel value is there, like 0 to 255. It is like, if it is 8-bit image, it is 0 to 255. Let the pixel value is 100. Let us say less than 100, you consider it black. Other than, you consider it white.
Just
Like that.
make 0. Anything less than 100, make it 0. So
Okay.
anything above that,
Yeah.
so make it binary. Binary is 0 and 1. You need to give one threshold.
So this percentage, the threshold percentage, are all like based upon the experience or just trial and error. We have to choose it. So all others are like ellipticity allowed. Like if the droplet size is blob or something, how much ellipticity is allowed? Like smallest allowed area of the pixel. Like you have to allow like only 3 pixel if you take. If it is like 1 pixel or 2 pixel, it can be noise, is it? Like if it is, the information is not, we cannot trust it. So only if we choose, like only if it is 3 pixel, we choose it. So after that, the code starts. So from here, all I said, like condition. So only between the droplet size, it gets the droplet data. From the droplet data, first droplet set, so there is a second droplet set. If it is between the area cutoff, you take it. This is between the like bounding box cutoff, you take it. It is between the X cutoff, you take it. All of them you take it. Finally, you get the velocity. So I have demonstrated up to this, like velocity, how you get the velocity. Like, shall I go, sir? PDIA. Value. And this is the threshold image. Previously, I was telling you. So whatever it is less than that threshold limit, it will consider less than that, it will be 0. Otherwise, it will be 1. Whatever is 1 is your white region. So now you have this white region. So you can, like, it is like number of pixels, is it? You can see like pixels are arranged. So if you know the number of pixels or the like area in pixels, you can get the diameter in pixels. Again, if you convert it into based on the calibration value, you get it. So all of them are going in the background. So this is one thing that we are getting from the file. Apart from that, this I have shown you earlier itself. What are all the focus droplets which are focused that it is showing, and velocity vectors that I have shown you earlier. This is while interactive mode, like it is different. Like there is some error, we need to set it up. So while saving, it is giving proper value. You saw it, is it? Velocity vectors, you saw it. So we can ignore this. So droplet size, I have processed only 2 data set. So we see like it is like histogram, like droplet size and microns in each bin, how much number of droplets are there. This side you get like the blue line, whatever you see is number of droplets. Let us say you see in like 150, 125 to 150, we have only 1 droplet is there. So it is like how many droplets in each bin, what is the number of droplets. So again, this red region, it is like what is the volume covered by each bin.
So it's just like here, since you're processing only one image, 1 or 2 frames, you have this number. So we just can't trust that data. So to get the total number of drops, you have to process enough images that you need to have at least 3,000, 4,000 or 5,000 number of drops. Then you get a statistically better number. So otherwise, so you will bound to get error. So when you do, don't take one frame and conclude based on that. You need to have enough drops.
So far we did like with the existing data. Now we will consider this data.
Okay.
Okay.
How can you follow about the assessment data?
So uncertainty in a diameter, two things.
Image processing.
Image processing is different. You can change the threshold. You give like inside of the event. So that is one thing. And same with the velocity, right? Velocity also with error by giving. You just change like a 10% variation in the threshold. Accounted for the because more than that, it changes 20-30% in the ground. So that is the
Is there any quantity or
and then the pixel resolution, right? So you have a pixel resolution, 20 micron. Even if one pixel is removed, you will get that. So there is a pixel resolution, 20 micron, is, you know, and then it was we have to tell the yeah.
we change the single case and like that.
So these are all in the background. Like I am saving set 1 and set 2 files. Now we took around 2,000 images. What I needed, like in sets. So if you see like first image. So if you see the first image, there is a first image. There is a second image. So it is the same droplet is coming as it even after 20 images. So what we can do is we can ignore it, take the first image, and go to the 20th image or 10th image. So what I do is, what is it? Why we need to repeat the same droplet, measure the same droplet. So what we are doing is skipping it. So skipping it, go to the second droplet. In set 1, it will like first frame, 10th frame, sorry, 11th frame, 21st frame, like that in set 1. In set 2, second frame, 12th frame, 22nd frame, we are going to save it.
Yeah, that is also like just now we discussed, right? We need to get statistically enough number of drops. But if you keep measuring the same drop 100 times, it is not going to change. Like if it is slow motion, so you take all frames. At the end, you get let's say 1,000 drops. But in actually there might be only 100. One is measuring 10 times. Each one is measured 10 times in different frames. That way, it should be enough across the frames. That we need to.
So I take only like I trim it like background. I am just it may give some like error in our generally this black region is considered as our droplet. So if you have outside, it may not sometimes it may not consider. So I am just taking the center alone. So again, I am saving this is the first frame I saved. Now I go to the second frame. Okay. From the second frame, I am saving. I skip each time the second one. Okay. Previously, I did not use the image processing for the first set of files. I am just going to do it again. So we have 100 set of images now. So you can see set 1 and set 2. Is it? Now we can check once whether whatever we see saved is correct or not. So set 1, first image. Set 2, second image. So you can see from here it moved to, from the first frame it was here. The second image it's slightly moved down. It is like here also you can consider, is it? Like this width is also moved. Slightly it moved. So if you want like the second frame, it is very close, but we will get the velocity vector anyway. Sometimes in the image from the first image, previously in the previous set, it was like very long. Now it is very close. So
If
so
you
can
feel that it is very close, you can skip 4 or 5, like first image, and then after 3 or 4 images, you can just.
so our frame rate now we took is 9,000 frame. So I kept 1 by 9,000. Scale is 20 microns, 0.02. So I am just going to leave it for now. I am going to just try it. Let me take only one set of file. So background, I have to check background is saved or not. So background is here, but background is not cropped. So I have to crop at the same place. So I am going to crop at the same place. Okay. Yes. So slightly it is changed. A small drop here.
Okay.
So we have this background file. We save it as BG. It is whatever already saved. So now we are going to run the code. Let me try running it. Okay. So we got only 2 droplets. Okay. Okay. 2 droplets are there. So the information we got is velocity vector. The velocity vector couldn't detect. It was very close. It was unable to detect, or the velocity vector is not visible at all. So it is like 2 meter per second. We have got the value, but it was very close. The velocity vector is not visible. So if you want to run for the entire set, it will take time, but you will get the final value. That's it.
It will be combined for all 100 images so that you get much better histogram.
You want to tell something? Okay. Maybe we'll see up to whatever process. This is an error. Actually, it requires a bit of troubleshooting. Sometimes we may need, if it is a new set of image, we may need a bit of troubleshooting. So what we can do is up to whatever it is processed, 8 set of data is processed. One thing is we can ignore if it is troubleshoot, like some set of image, if it is giving like error, you can ignore it. Otherwise, you can just like for now, what we do is with the 8 images, we will see what we got. Only 8. Yeah.
8 drops. So you have one drop, right? So why don't you run that where we have a lot of images, a lot of drops, right? Only that.
Oh, yes. Sir. So 8th image, I think there is no data. That's why. Oh, we can start from some 41 to around 52, or else 31 to 52. You can see processed image. You can see it is getting loaded one by one image, it is getting saved. So it is C velocity vector is also there. It is very small. Yeah. What again, like you are not seeing velocity vector because it is not focused. Only if it is focused, you will see the velocity. So you see here, one droplet is focused. Maybe here see 3 droplets. It is focused. Yeah, it takes time around 30, 46, 47. So we gave up to 52. So processing is done. So you can see the total only 8 droplets. Okay. So 40 droplets, we have accepted 40 droplets out of total 359 droplets. Based upon this threshold limits and other things, we have accepted 40 droplets, out of which only 8 droplets were total accepted for droplet like trajectory. Okay. So you have all these values, DCV10, DCV50, DCV90, and SMD you got 290. Whatever we saw here, it is like Sauter mean diameter of the droplet is 290 microns. That is what we got. And also we see the, what is it? Velocity.
Average.
Yeah, it is velocity is 6.3 meter. It was like distribution.
Yeah. But
So distribution, you saw it already.
Yeah.
So what is the distribution here? It is very close, like 125 to 300 microns. Whatever we saw is 125 to 300.
You can, yeah, this is our process again. No need to use a high speed camera. Also, you can use simple camera if the things are not moving very fast. So, right. So this is how we do this PD. We call it as PDIA. And if it is only size, it is called PDIA, particle droplet image analysis. So because you can apply this to any solid particles also, no need to have any drops. So there is no refraction, it is just a shadow. And if two frames are analyzed, usually it is called a velocimetry, particle tracking velocimetry you're talking. So this is about it. Yeah, we will close here. If you have any doubts, you can ask. Otherwise, we close this session here, right? So tomorrow we see, like, if possible, we can have a PI visit. Okay. Yeah. If not, so what we do is we'll see like how to illuminate and maybe take some images and process and show like images. Okay.